Okay, so let's continue. And now we have the last lecture of Dr. Jack Lissauer, so let's enjoy it.
Thank you, Marcella. Before I begin, since this is the last lecture of the school, I think the school has been extremely well put together, well arranged, well organized, and I think that we all should give a big hand to the organizers, especially Isa, Marcelo, and Vinicius. Okay, I gave you the info on Kepler mission in the sense of the spacecraft and the launch and the instrument, one instrument, a wide field of view photometer. And I ended my talk yesterday afternoon on this slide, which shows the planetary candidates as of end of 2012. This is the stars, correct proportional size, correct color, according to the nominal Kepler star catalog, and the catalog has gotten a lot better since then, so there's not quite the same range of properties. They're all Kepler planet candidates aside from this, which is the Sun and Jupiter. So some big stars, some small stars, some blue stars, some red stars. Some of them you don't see planets because they're just so small. Kepler is a very sensitive photometer. Some of them you see 1, 2, and 3 in this case. There's some with more, but it tends to be small planets that are in high multiplicity systems. And this is the next round, a little over a year later, over 2,700. And in the next round, which were announced, this is inclusive of the previous ones. At the end of 2013 in November, it was up to over 3,500. And it's now over 4,000 and counting, but there's no real good catalog beyond the 3,500. These are the locations as of that last one. They're all over the CCD, all over the field of view, not all just near the galactic plane or farthest from the galactic plane where there's least crowding, so we're seeing a lot. And these are coded by the size of the planets. Earth size, super Earth size, Neptune size, and giant planet size. And this is that last catalog that we have. And this shows them a little differently. The colors are the ones added in the last catalog are in yellow. The ones prior to the last catalog are in blue. And Jupiter size, Neptune size, Earth size. I think these are either not planets or their sizes. The ones that are near the top are either not planets or the sizes are wrong because the stellar properties are wrong. We're getting better at that. You see down at short periods, you have many planetary candidates that are smaller than Earth. At longer periods, you don't. The reason for that is not necessarily nature, but we need at least 3 transits to get a planetary candidate. Takes a while, but with the big planets, 3 transits is enough. Whereas with the smaller planets, we need many transits because the signal to noise is not good, even with Kepler data. Because we're talking about planets who cause a drop in the signal received by the Kepler photometer of less than 1 part in 10,000 for only a few hours once in orbit. And what we do is we fold the data at all different periods, possible periods, and search those folded data at all the periods. That's why it takes a long time. But that allows us to get many transits when you couldn't see a single transit, because the noise would be there. It would be no bigger than a star spot. This is a massive effort, and this is only a small portion of the people who worked on the project. Bill Barucki has been working on this project for about a third of a century. Now, I've been talking about planet candidates. Why am I saying planet candidates rather than exoplanets? I am being a little bit haphazard sometimes. I'll say planets when I'm really referring to candidates, but most of them are still candidates. And the reason are these pesky binary stars. Because if we have this periodic signal causing dips, well, that type of clock is really something orbiting a star. But stars can orbit stars. Now, the difference is stars are usually bigger than planets. The very biggest planets are a little bigger than the very small stars. But in most cases, stars are bigger than planets, and therefore would cause a bigger dip. However, it could be that it's not an eclipse near the center of the primary, but rather just a grazing eclipse. Actually, what this does is it causes the light to gradually go away and then very gradually come back in. So these we're not really that worried about because our light curves are so good. But these guys, where it's a background binary that's much fainter than our target star, and this could either be a physical triple star system, or it could be just a chance alignment blend with a background binary. And these are a much bigger problem. This is our first few dozen planets. Some of them are somewhat bigger than Jupiter. These are all close in, so they're inflated by the heat of the star, heat from the star, maybe tidal forces from the star too. All we know is their size and their orbit. So the colors are just arbitrary, except for the fact that for planets around the same star, the same color is used. And at this point, we had one first planet around a normal star other than the Sun, smaller than Earth, to be discovered was Kepler 20e. We see some planets bigger than Jupiter. Almost half of the ones here are bigger than Neptune. And most of the ones that are smaller than Neptune aren't that much smaller. And there are systems of high multiplicity here. Kepler 20 goes to F. Remember, there's no A. A is the star. So that means there are 5 in that system. Kepler 33 also goes to F, so there's 5 orbiting that star. And Kepler 11, the one I showed you the diagram of last time, goes to G, so that means it has 6 verified planets. Now, this was before Kepler 37, which has 3 planets. One is about twice the size of Earth. One a little smaller, and one smaller than Mercury, very comparable in size to Earth's moon. And these are artist conceptions of the planets. All we know about is their size and location, and the star they orbit, which is a little smaller than the sun. We have good properties on that star because it was it's a very bright star for Kepler, and therefore we were able to see the oscillations and do seismology of it. They're pure artist conceptions. This one, big enough that we have some planets that size where we have masses and they are too low density to be rocky, so it's depicted as a cloudy world. This one, very small, close in, hot, almost impossible to retain an atmosphere, so depicted like Mercury or the moon. And this one's kind of intermediate, maybe some clouds, but not a lot. Kepler 16. I had a question yesterday about or planets in binary star systems, and I noted that for circumbinary planets, Kepler is the best instrument out there, and this is the first circumbinary planet we found. The star a little bit smaller than the sun, one only about 1/5 the size of the sun. They're orbiting each other in a close orbit, and they're being orbited by a planet that's about the same size and mass as Saturn. And if we had a top view, this is what we'd see. 2 stars orbiting one another in a close orbit, and the planet orbiting the pair, orbiting basically the center of mass of the pair. And it's far enough away compared to their orbit that its path is pretty close to elliptical. But by seeing the transits, let me do that again, by measuring the times and durations of the transits, we get the properties of the stars, the pull of the stars on the planet. And by measuring the slight variation in eclipse times as the stars eclipse one another, we're able to see how much pull the planet has in the stars, and therefore get very precise estimates of its mass. The effects the stars have on each other and on the planet allows us to get much more accurate estimates of the stars' properties, and that helps us give us the size of the stars included among those properties, and that gives us better information. The size of the planet, then the pull of the planet on the stars gives us the mass, so it's a very well characterized planet. Here's another graphic. This is a little more artistic. We see we're starting with the planet. We don't know how it rotates. We don't know what the clouds are like. And then see the stars as we move away from the planet, and see the eclipses and moving out. And we're seeing now more from the perspective that Kepler is seeing those eclipses transit the planet, the eclipses of the stars. And again, this is artistic, but we know from spectroscopy, the spectrum of the brighter star, we know what the fainter star must be because of its size. And we're getting these primary eclipses, secondary eclipses, and they're not completely periodic because the perturbations of the planet. And this is the light curve. We see the primary eclipses, the secondary eclipses, the planet transiting the primary, the planet transiting the secondary. We can't see the planet occulted by the stars, but the planet's not that close to the stars. That would be extreme sensitivity, even by Kepler standards. But we can see 4 different types of events here. And that's why we're able to characterize the system so well. And a lot of art, here's another art of a transit occurring at the time of an eclipse. We've seen a few more. It's now up to close to about 10 of these circumbinary planets. Here's another one where the stars are more similar to one another in size, also a Saturn-like planet. So I mentioned the planet candidate, they're planet candidates. And that one of the big sources of false positives that we have a difficulty in discerning, to weeding out in other ways, is background eclipsing binaries. But if we look at where the planet candidates are in the field, and we do a plot of how many of various types of objects are closer to the plane of the galaxy than whatever this galactic latitude is here. This is basically things less than 5.5 degrees. The fraction of objects is 0 because everything is less than 5.5 degrees. Here it's 1 at 21.5 because then we have the entire field. This aqua curve that I hope you can see, nice smooth curve, is the Kepler targets. And it goes up slowly here because we're just touching the bottom Kepler field of view in galactic latitude is something like this, and this is 5.5 degrees. This is 21.5. So we start, as we go up in galactic latitude, we've got a very small piece, even though it's a little denser in stars. It's just very little area at the lowest galactic latitude. Then we get more, so the slope steepens, and then slope is shallower because we have less area at high galactic latitude, plus there's less density of stars. And the number of planet candidates, both singles red and multis black. Multis are when there's more than one planet candidate per star. Track very well the targets. Whereas if they were mostly background eclipsing binaries, those would be much more concentrated near the galactic plane, because what we need to have for background eclipsing binary is a background binary near where a target is. So the density of those is much higher, but fraction of them is much larger near the galactic plane because it's kind of quadratic. It's it's the product of the targets and the background. And this is the theoretical curve, this dotted curve, and indeed the false positives that have been identified as background eclipsing binaries follow that curve, whereas those that are thought to be good planet candidates follow the target curve. So that suggests the sample in general is pretty good. And there are other things that suggest the sample is generally pretty good. About 90% of the candidates are real planets, maybe even a little more. But that's still not enough for us to call them all real planets. Okay. Now, I'm going to give you a little bit of a statistical argument, but it's an important one. And it demonstrates that most of the candidates in multis are real planets. And over 40% of the candidates we have are in multis. And this statistical argument has been the basis for verifying most of the Kepler planets have been verified, over 700. So about 40% of the planets known have been verified by this statistical argument. And by known, I don't mean Kepler planets. I mean planets that we know of, anywhere. So there are about 140,000 high-quality Kepler targets. And this is the numbers as of a while ago. You have to use a coherent data set. And therefore, I don't throw in new numbers as they come in, because we have to verify everything in great detail. And it's better to use old numbers where we've done that than new numbers where we haven't. Of those, 1,700 had very good Kepler objects of interest planet candidates as of 2013. So a little over 1% of the target. Now let's just assume, based on some arguments that I don't have time to give, about 10% are bad. About 10% are false positives. And let's assume that eclipsing binaries, these nasty things that masquerade as planets, are randomly distributed among targets. You just toss them to different targets. Then the fraction of targets near an eclipsing binary is about 1/8%. So 1/10 of a little over 1% is about 1/8%. And that means the number of targets with something bad is 172. So that's a pretty big number. It means 10% junk. We don't want to verify things with 10% junk. But if you just look at ones with one planet candidate, one other planet candidate, what's the chance that there's an eclipsing binary? Well, only 0.123% of this number, 1723. So there were 1723 with a good planet candidate, but only 3 of them would be expected to have also another planet candidate, good or bad. So one bad one and one good or bad one. You'd only expect 3. So you'd only expect, if all these were just randomly thrown out, you'd only expect 3 cases where you have a false positive together with one other planet candidate, be it a false positive or a real planet. So 3, and you can do it in a slightly different way and get 2. But we observed 410 at that time of these multis with over 1,054. So you'd expect background binaries to be just randomly distributed relative to one another, but you could have a bunch of planets in the same system because, as we see in our own solar system, as we've seen in some of the first Kepler systems verified in other ways, there are flat planetary systems are common. And therefore, if you see one planet transiting, it's not that unusual. It's not random that you'd see another one. So this says maybe 2 or 3 of these 1,054 Kepler planet candidates in multis should be bad candidates, should be false positives. Well, that's 99.7, 99.8%. That's 3 sigma. So almost all of these planet candidates in multis are real planets. Yes?
Just one question. Is that number 172
Yes.
based on the ability of Kepler to detect by itself false positives?
Yeah, well, the 10% is based on the ability of Kepler to detect false positives, but by the work that was done with Kepler data. Because when we actually, I didn't mention this, we send back not just one picture element. Kepler takes images. We can't send back the complete images because that's too much data, but we send back a few dozen for each target. And if we have a transit, a background that's not right aligned with the star, then it would be, the center of light during transit would be moved from outside transit. And that would show us that would be a false positive. So it's only the ones that are really close. But from these studies, we can predict how many you should have.
Okay, so the real question is, so there is no possibility that the number of 0.123% is biased by the capability of Kepler detecting false positives?
This is a very conservatively estimated number. Okay, so most of these multis are real. And what we've done is we've used them to try and discern properties of planetary systems. We've looked at the period ratios of neighboring planets. For instance, Earth is about a little over 1.5 times the period of Venus. Venus is a bit over 3 times the period of Mercury. And if there's a lot of migration, you could see planets getting stuck in resonances. And there is, incidentally, there are peaks, especially in the 3-to-2 resonance and the 2-to-1 resonance, but not inside. Inside, there are actually somewhat gaps. So few planet pairs are in resonance. But if you had these as they weren't real planets, then you'd have a lot of just random chance alignment where you'd have very similar periods. But you don't have many with very similar periods. If you had random pairings, it would be like this. Very smooth and a lot at similar periods, just because they're common periods at which Kepler finds planets. And there are only 2 that are really close. So if you had random, you'd have 56 pair that were real close and nominally unstable because they'd be perturbing each other too much. But there are only 2 that are bad in that regard. Now that could be because one is a background binary stars, or it could be planets around 2 stars that are different but physically bound. And with one of these, there are problems besides the periods with the planet candidates. They're not very good candidates. But for the other ones, what we see is a double star, binary star almost identical, we have velocities that are moving at about, they're 450 AU apart on the sky. Their velocities are correct for them being bound. So almost certainly one of them has one of these planets and the other one has the other planet. So this is a nice artist's conception. There are all these multiple transiting planet systems out there. Now, let me go into detail on a few of them. Kepler 9 was the first system with 2 planets transiting, found anywhere by anyone that was verified. And these turn out to be about the size of Saturn, but only about half the mass. This is the light curve, measurements of light every 30 minutes for the first, 9 months or so of the mission, 8, 9 months. There are a few data gaps when they were downloading data. You can see transits, one set that's a little deeper, one set that's less frequent and a little shallower. And if you line up the transits with a period, constant period, the best fitting constant period, since these are giant planets, we have very good resolution. You see that they don't line up correctly with a constant period. They're off by, well, tens of minutes. And this one, it's over an hour or so. Different colors represent different transits, individual transits there. But if you do a model where it's not just planets in Keplerian orbits, but take into account gravitational interactions between the 2 planets, changing their periods slightly, exchanging energy back and forth between the 2 planets, then you can get a self-consistent model where everything lines up very well, as seen in the bottom panels. And then there's this little inner planet, which is separate. This transit timing variation, we take a simple constant ephemeris of constant periods and compare that to what we see, and we see that planet C is earlier at the beginning, then later at the end. Planet B is later at the beginning, earlier at the end, and less of an amplitude. If we, instead of using this calculated with constant periods, allow the planets to have mass and to interact with one another, we can do a simulation, and instead of having errors of from 20, 30 to 80 minutes, we end up with uncertainties, with errors which are typically 1 to 2 minutes, which are less than the uncertainties because we have a limited number of photons. So we get a wonderful fit, and this not only confirms that these are planets orbiting the same star, but it allows us good estimates of their masses. That was Kepler 9. We were on a real roll there. Some major firsts. Kepler 10 was Kepler's first rocky planet. This is a very close-in planet. orbital period of under 20 hours. Yeah, real hot. And about 1.4 times the radius of the Earth. And this target star was one of the brighter stars for Kepler. So it was possible to detect this planet also by radial velocity variations of the host star. So we could confirm it by measuring its mass, and measuring its mass by radial velocity. So we used different techniques. There's a more distant planet in 45-day orbit, but we don't know a lot about that. It was verified by statistical arguments, looking very carefully at the environment of it and details of the light curve, but we don't have any gravitational measures of it, other than upper bound. It's a little larger, and it probably is not rocky. Almost, it isn't rocky. It's certainly not a pure big rock. So this is an artist's conception. It's a tidally locked planet, so one hemisphere, really, really hot. Lava world. Kepler 62, I'm jumping around a bit. But this one is of particular astrobiological interest. Has 5 planets. The star a little smaller than the sun. These were not they're not big enough and close enough to one another or to resonances to perturb one another in substantial ways. So they were verified by other statistical means. But the key planet here, most interesting one, is this guy, Kepler 62f, which is about the size of Kepler 10b, only slightly larger. Now, it's a lot farther from a star, but still we've seen rocky planets that size. These are all artist conceptions for the Kepler 62 planets. But this guy, that's the size of Kepler 10b, and therefore small enough to be plausibly rocky, is in the habitable zone of its star. So all planets, all exoplanets known, this is the one most likely to have conditions suitable for life as we know it. There's only one that's any competition, and that's a little smaller, but around a redder star, and that's Kepler 186f, which was discovered a lot later. That's why it's a higher number. This is a these habitable zones are very, very liberal, so that's why Venus is at the inner edge of this one. Good, it doesn't even show up very well. Venus is at the inner edge, okay. And this 62E is at the inside the just outside the inner edge, but not 62F. That's the interesting one. It's smaller also. Again, jumping around in number, but this is really a phenomenal system because the planets are in 10 and 13-day orbits. They're very close. And they're perturbing each other substantially. And there are 2 sets of transits, but one set is really all you see unless you look really closely. Because all these down here are the same planet transiting, and it's just up here that you see the other planet transiting. And this is the transit depth, many transits put together, of shallow interplanet transits. This is the transit depth of the outer transit planet. And this actually, the outer one was seen, and it was seen that there were substantial timing variations, so something was perturbing it. and a special detailed search was made. A special algorithm that found the inner planet. And this is what's called a river plot. And this shows the transits, which are the blue, and barely blue here because the transits are so shallow. Beginning and end of transits marked by red, added by I later. And this shows how the times of transits vary by 3 or 4 hours. The gray means we don't have data. We're downloading data or something was wrong. But it's beautiful to see one go ahead while the other goes behind and vice versa. And you might have noticed, if you're really paying attention, that the sizes of the planets were very different. The depths of their transits were very different. But the amplitudes of these variations aren't that different. And that means we have two planets similar in mass, but very different in size. And the inner one is substantially smaller, and it's rocky because we were able to measure their masses from these transit timing variations. The outer one, most of its mass is probably rock, but most of its volume is hydrogen and helium gas. And this is a hypothetical view from Kepler 36b, the inner planet, where Kepler, at night, looking out at Kepler 36c, which is a gassy world, which would be huge in its sky. It passes. It laps ahead of the planet on the farther orbit. These transit timing variations were used to confirm dozens of planets in a few years, especially in 2012 and 2013, when people got the method down. One planet getting ahead, one planet getting behind, in some cases by things like 10 hours. Kepler 30b. This is done less now because we were able to verify them using statistical arguments by many hundreds. Now, I will go back and give you a lot of details on Kepler 11. This is the 6-planet system, which was the front piece. This is the front piece of the talk. And again, planets are correct in relative sizes in this graphic, but they're enhanced by a factor of between 2 and 3 compared to a star, just to make them visible. This is where it is in Cygnus, sort of near the edge of our field of view, but not an extreme. And here is the light curve for 1/4 Kepler. When it observed its regular field, had to rotate 4 times a year to keep the sun from going into the telescope and to keep the solar panels pointing towards the sun. And therefore it was a 4-fold symmetry in its design, and things were observed in different ships every 4th quarter. They came back to the same ship. And this is 1/4 of data, 3 months. And these are the transits are marked, different depths, different periodicities, different durations. 6 different colors are used for the 6 planets. You can see some of them are substantially larger than others, and some of those arrows come in a lot more frequently because they're shorter period. And indeed, the shorter period ones tend to be the smaller transits. The shortest period 1b with those yellow arrows we couldn't have detected at that time. It's actually the last of the 6 to be detected. But it was still detected before we announced the system, so it's named B. Because it's smaller. It's so much smaller. So we need a lot of transits. And this is just showing a little more about the light curve we have. The flux we get actually varies by a couple percent, 2-3%. And these big discontinuities are from quarter to quarter. And I mentioned earlier on, this is photometric precision, because all we care about, we can take out long-term trends. We want to see characteristic signals on a period with durations of a few hours to 15 or 20 hours, the transit variation. So Kepler is designed to minimize phony variations, sources of noise, at those period ranges. Because we just take out the long period variation. It doesn't matter to us. We don't have accurate photometry, we have precise photography. In other words, you're getting differences from one time period to the next, the next, the next, over time scales of hours to a day or so. Not over time scales of months. You do a different spacecraft design, you'd be sacrificing something. These are the data. You remove the long-term trends, and now the transits become more apparent, and they're marked here. Periodicities, different planets. And again, the arrows pointing towards where those transits occur. This is the time when 3 planets were transiting at the same time, and those 3 planets, their relative positions are correct on that diagram. This was the motivator for that diagram. Right. This is a view. You see, this is what Kepler's seeing, except greatly exaggerated, the blinking of starlight. And what we infer from it is there's a system of 6 planets going around. This gives their correct relative periods and their correct relative sizes, and this is what it would look like from the top. We are in the plane of the planets. This would look like from the plane, from perpendicular above the pole of the planetary system. So let me do that one more time. The blinking, greatly exaggerated so you can see it. What we get if we got very close to the system. That one planet is indeed transiting near the top of the star, and then the outer plane view. Now, not only do we see 6 transiting planets, and this is the transits of many times put together of the planets, but we see, this is a different view, a different type of graphic, same scheme. So these are the transits, but they're not quite periodic. And we see slight variations in the transit times of all the planets other than the outer one, for which we only had 3 transits at the time, and even with all their transits, there's no clear variations. And in some of these cases, there's pretty significant patterns of variation. And up here, and the colored points are data. The diamonds are a model based on mutual gravitational interactions of these inner 5 planets. The 6th one is much farther away. The inner 5 have periods ranging from 10 to 47 days. The outer one has a period of 118 days. And from these transit time variations, we can confirm that they're planets in the same system, and we can estimate their masses. This shows the gravitational effects of individual planets on other planets. So this one, the inner planet, the yellow one, is primarily affected by the red one, its neighbor on the outside. The red one is primarily affected by the yellow one. The blue one is affected primarily by the green one, the one outside, a little bit by the red one, the one inside it. The green one is affected primarily by the blue one, but non-trivially by the aqua one. And the aqua one is affected almost exclusively by the green one. And this one, this is half a minute. We don't have that precision. You need a much bigger telescope for that. This is just a numerical integration of the system, showing that it's stable for the entire time. We actually extended this for 1 billion years. I just don't have a plot of it. And this, before that, we just had Kepler 9, Kepler 10, 2, 3 planets, and this was 6, so it was a big deal. Plus, we had measured densities for 5 of these planets. And pretty amazing, because the densities, the radii were small. These are a little bit later measured estimates of the density and radius, but they're 1.8, as small as 1.8 Earth radii, but densities are much less than rocky planets, all 5 of the inner ones. So it's possible that this one could be a water world, part water, mostly water, but some rock. But all the other ones certainly have a substantial volumetric amount of hydrogen and helium. And the inner one could also be hydrogen and helium. Hydrogen and helium for planets that size, there's very little mass. It's only a few %, but it's still dominates by volume. So the mass has to be provided by water or rock. And we just didn't know about these planets at all, inner planets, or planets that small, that were mostly gassy until Kepler 11. This, at the time Kepler 11 was announced, this was the plot of mass versus radii for all the planets smaller than 20, or I guess 30 Earth masses. And if we look just down at smaller than 20 Earth masses, well, we've got some solar system planets, these triangles. We had Kepler 10b. This was a Corot planet, the small French spacecraft, larger uncertainty, because it was a nastier star. This was a planet discovered from the ground around an M star. So you have these 3 exoplanets, and then 5 Kepler 11 planets. Now this is the plot. For a little smaller region, this only goes out to 20. And the solar system planets, and then the planets, anything with a solid symbol is Kepler. And the one I mentioned in my talk, Kepler 36, Kepler 11, Kepler 10, are with are noted with numbers on them. But anything with a solid symbol, which is most of the exoplanets, the vast majority, are Kepler. And this also shows how hot they are. The really hot ones, where an atmosphere could easily boil off, are the reddest ones, and then the yellow ones are still very hot, 100 times as much energy from their star as Earth receives. So these are all warm. Even the green ones, Kepler 11 ones, are green or yellow. Even the dark green ones are still more than 10 times as much energy as we get from the sun. So it's still pretty warm. We're working on some cooler planets. This is a scale model of Kepler-11 system compared to our solar system. The 5 planets are closer to Kepler-11 than any planet is to our sun, and they're all at least 1.8 times the radius of the Earth. 1.8 times the radius, wow, you know, that's 6 times the volume. So these are pretty big planets. And some are bigger than Uranus and Neptune, although they're less massive, a little less massive. And even the outer planet is just outside Mercury, would just be outside Mercury's orbit. Very compact system. And this is just another view of the masses and radii for the 5 inner ones, and the other planets known at the same time. Some of these graphics are those developed, these artist graphics are expensive to produce, so we have them for press conferences. So this was at the time of the Kepler-11 discovery. The summary was Kepler-11, very flat. The inner 5 planets, if you built a scale model of it, it would be like a compact disk. If you include the 6th planet, it's so flat, it'd be like one of those old, long-playing phonograph records, vinyl. A few years I won't be able to use that analogy. This is very closely spaced, so we're seeing perturbations, and we're able to discern the masses. Planets are medium size, from a little under 2 to a little under 5 times as large as Earth, and they have low densities, implying they have a lot of gases in there. They're not big rocks. None of them are big rocks. The idea that you have super Earths that are twice the radius of Earth, well, those, there are probably some of them, but they're very rare. Kepler has shown that. It's very rare to have planets bigger than about 1.5 times the radius of Earth. They're rocky. And Kepler-11 has, I don't know if you have them here in Brazil, but these games, this is a field of corn. And as the corn was growing, they mowed some parts, they made a maze. And a Kepler-11 diagram and the graphic of the Kepler spacecraft and viewing the Kepler-11 system, NASA finding new planets, 2011, and then this stars all around, and a pumpkin because this was at harvest season. They invite families there, and they have all sorts of games and things. It's very child-oriented, but fun for the family. Zip lining, I went zip lining there. And this is the people who put it together. This is the town, and this is where they put it together. But anyway, it sparked a lot of creativity. Okay, let me get into some more recent numbers. This is from the latest catalog, over 3,500 planets. And these are candidates mostly. We've verified almost 1,000 now. There are 464 systems with 2 candidates. So that's over 900 planets. Almost 450 with 3 planets in systems with 3 candidates. 200 planets in systems with 4 candidates, 100 in systems with 5, 24 in systems with 6 candidates, and 1 in a system with 7 planet candidates, and that recently has been verified that they're all planets. So that's now the record holder. Kepler-11 with 6 is second, and there are a bunch with 5 in terms of verified. This is a modern version with that catalog of the planet radius diagram, but this is also noting the multiplicity. So different point types signify how many planet candidates are in the system. And you see again, this is there, it's not blocking anything. There's one planet candidate here, but this turned out to be wrong. This would be nice because it would be near Earth in size and radius. It's not real. Things around here are a little less trustworthy. Because obviously something like this people looked into in great detail. And almost all the multis are likely to be real. It doesn't mean that their sizes are correct though. Because if it's just a candidate, it means we don't know nearly as much about the star. And in some cases, we're off by a factor of 2 or more in the star size, and therefore in the planet size, because these planet size estimates are based on the transit depth and the estimated star properties, and we have to look into the star properties a little more. The only thing we have for all the Kepler targets are what's called the Kepler input catalog. And it was an input catalog because it was designed just to choose which targets. This is from an older list, but systems with 3 or more candidates, organized by the period of the inner planet. And the biggest one for each system is red, then orange, and then green, and then aqua, and then blue, depending on how many objects are in the system. And the planet size, candidate sizes are proportional. It's the same thing for everything. And we can't even fit it in a legible manner on one view graph. So it's just pretty amazing. Let's do that one more time. And this is just the system with 3 or more candidates. Now, this is similar. This is something Dan Fabricki created a couple years ago. These are scale models. Again, the periods and phases are correct to scale. The planet sizes are to the same scale for each system. This is Kepler 11. I can tell because it has a color that nothing else has. And it had the most at that point still in terms of candidates, 6. And this is just the duration of time elapsed as the spacecraft went around. Now, we're not taking data from individual days, but this is the ephemeris calculated for each of the planets, each of the planet candidates in multis. It's really amazing stuff. By far the majority of, even just including the ones that have been verified, of multiple planet systems known, 80% are Kepler systems. And these are the numbers, the Kepler object of interest number. So Kepler 11 was KOI 157. Kepler 90, the 7, now it's up to 7, was KOI 351. Just when it was identified as planet candidates versus when they were verified. So I would have shown you that, but I have a more recent one with the latest list. And I'm going to show you that one. Dan Fabricki chose some nice music for it. I mean, it really is pretty grand. And the small systems are the inside, small by the smallest orbit of the outer planet. You can barely see some of them, but we can zoom in later. You can see there's a vast variation in planet sizes. We now have so many high multiplicity candidates. This is the only plot. It is on one, but it's only the systems of 5 or more candidates. And some of them have planets out to a few hundred days. Turned out those 6, this is organized by periods of the outermost period of the inner candidate. Here's the period ratios with a more recent diagram. Again, very few in this unstable. The 2 in the unstable, 2 bad ones were removed in this, and everything else looks stable. So all evidence that almost all of them are real. And there's a little enhancement on the wide side of resonance. This is now a more recent one. Near some resonances, there's these gaps just inside resonance. And what causes them? Well, it's probably interactions between the planets, and maybe it has to do with tides. How much time do I have? Because I don't want to.
15 minutes.
15 minutes to talk?
Yes.
Okay. I have a few things that I want to add, so I'm going to skip the resonances. But I want to say a few things about some other types of systems. Kepler 80. This is the scale model of Kepler 11 and Kepler versus the solar system, showing how compact. But this is KOI 500, and the periods there go from under a day to 9.5 days, so all shorter than the innermost planet of Kepler 11. And this is a diagram of KOI 500 on the same scale as to these others. So this, they have shorter periods, and it's even smaller because they're going around a smaller star. So this entire system fits well within the innermost orbit of Kepler 11. It's a smaller star and has a real shrunken planetary system. 5 planets. Here's one where I said there aren't that many commensurabilities, but the ratio of the period of the second planet to the first one is almost 4:3, almost exactly 4:3. The third one to the second one is almost exactly 3:2. Fourth one to the third one is almost exactly 4:3. So these aren't coincidences. There's interactions, and they got stuck there after migrating around. Must have. So there's now multiple planet systems are now on a firm statistical footing. There we found new types of planetary systems, compact, close in planetary systems where the planets are perturbing one another. They're very flat, and the multiple planets in some cases allow for easy interpretation of transit timing variations, and we're using them to derive more and more planetary masses. Now, this is one I showed in my lecture yesterday morning, and this is the radial velocity planets. Most of them are comparable in size to Jupiter or larger. And then we still have a bunch of Neptune mass and larger, and these are minimum masses, and not many down here. And these are 3 Earth masses or less, just a few. Kepler planets, this is as of over 2 years ago, about 2.5 years ago. And it was mostly roughly Neptune size, but a significant number of super Earth size. And super Earth size, This was a category, we didn't know what was rocky. Well, it turns out, if we did it now, super Earth size would probably only go up to about 1.5 Earth radii. If we were to define it now, because bigger planets tend not to be rocky. Now this is as of 2.5 years ago. This is as of 10 months ago. So just seeing Neptune size dominating, not that many Earth size. Now the big change is in the Earth size and the super Earth size. Virtually nothing at the big size, because they were seen right away. And in another year or two, another catalog, the final catalog, these are going to continue to grow the most. There'll still be some growth here, maybe a tiny amount here. I suspect that this will shrink because some of them will be found out to be bad candidates and some will be found out to be a little smaller and in this Jupiter-sized bin. But the numbers in general will grow, and it will be, I don't know if these will quite catch up with this one, but it'll be pretty flat among these three. Yeah. Small planets are numerous. This is I showed before yesterday morning, where if just the high precision radial velocity, you actually get the most of small planets. This is Kepler early on, where it was dominated by small planets, and it's even more so now. These are the ones, near the habitable zone. Kepler, there's a new one now, Kepler 186F. And this one, 22b, is pretty big. It's not habitable. Kepler 69c and 62e, they're really pushing it a little bit, both in their size and how much energy they receive from their star. But Kepler 62F really has some potential, as does Kepler 186F. Again, just reminding you of how different in size the giant planets are from the terrestrial planets. Detecting an Earth-sized planet, this isn't the Venus transit, this is one seen at a great distance. Real small spot, and we're not getting images like that, we're just getting the flux. So that's why we had to go about the atmosphere, because our goal is to detect Earth's true Earth analogs. And this is a simulation from a relatively bright, but a star, like our top 15% of the stars. And this is what a transit Earth-like planet looks like. And this is just a sunspot or something like that. The simulation includes instrumental noise, photon statistics, and actual solar variations, because we didn't have anything like this for stars. And you see, well, you can have transits. These things look as deep, the random as deep as the actual transit. So you can't detect these, you can't tell these from noise. But if you fold the light curve at the right period, then you get a signal which is unmistakable. Now, folding all these light curves at all these different periods, because we don't know the years of the planets, and looking at all different phases, mean we're doing 10 to 12, a trillion tests. And that means for statistical significance to only have one random false positive. You don't go for 3 sigma, you don't go for 4 sigma, you got a lot of those. 5 sigma, you got a lot of those. To get your random false alarm rate down to 1 in the mission, you go to 7.1 sigma to get to 1 in a trillion false alarms. Anyway, this is why we don't have it yet. We need all 4 transits, and we need to really work on the data, because it turns out stars were a little noisier than we thought they would be. Scientists are a little quieter. Didn't know. We've had another launch of spacecraft half as expensive as Kepler to find out. So whether we're going to get this, we're not going to get a lot. We may well get 1 or 2 true Earth analogs. We're not going to get good statistics. We're going to get much closer than we are, and we're going to be able to extrapolate. Rough numbers now, with some extrapolation, but much less than by any other mission, is that there are 1 or 2, maybe 10 to 20% of stars have planets roughly the size of Earth, sun-like stars, with periods within a factor, within maybe 50% of Earth's. So that's good. I mean, things, it's based on planets that are a little bigger. But if this extrapolation holds, we should have 10-20% of stars having Earth analog planets in terms of size and orbital period. Well, I asked what's next. We're going to continue studying the Kepler data. We're not done yet, even though we're not taking data on the primary field, because we had 4 reaction wheels, basically the gyroscopes, and we needed 3 to point at our field, and 2 broke. It's a low-cost mission. Yeah, we could have afforded more gyros, but we didn't know gyros would be the problem. And if we had super extra redundancy on everything, then it would have escalated our costs by an amount that we might not have been chosen. So we were designed to last at least 4 years. We lasted 4 years to the day when we started taking regular science data. So the last year has barely been analyzed. We're really working on it in great detail, because as you saw earlier, the data are noisy and they have to be processed substantially. And we're going to get a lot of great exoplanet science, including figuring out how big a planet, what size planets tend to be rocky and what aren't from these transit timing variations, and getting better abundances of smaller planets out greater distances, including hopefully true Earth analogs. And people are doing some spectroscopic study in transits of planetary atmospheres, but Kepler targets tend to be a bit faint. So they're not ideal for follow-up. Because Kepler, even though its field of view was huge compared to HST's, it was still only a 400th of the sky. So what we're doing next is, in about 3 or 4 years, we'll be launching TESS, which is a smaller spacecraft, but with a much larger field of view, and which will point at different fields. Kepler's also looking for short periods in its orbit, because then it only needs 2 gyroscopes. But looking in its orbit means it will be looking at the sun part of the time if it didn't switch fields, so it can only observe the field for 80 days. So it's not going to get small planets in the habitable zone, except maybe for very faint stars or M-dwarf stars. But next up is this small telescope, a very wide field of view, and it's going to be basically all sky survey. Not as long period planets, not quite as small, but we should be able to get some great information. And this just shows the small and kind of deep but focused, generally farther away, Kepler search space, 400 square degree field of view, compared to TESS, much closer, much brighter stars, out to about 200 light years instead of 3,000, with a 40,000 square degree field of view, essentially all sky. So it will get the best. Kepler has been producing, will continue to produce great science. And some ground-based follow-up to better understand the stars, et cetera, is helping that. But Kepler's producing it. TESS will be more of an enabler because it will identify the planets that you can study with JWST and ground-based telescopes to get spectra of atmospheres of transiting planets. So I'm going to wrap things up. At present, there are almost 600 targets with 2 or more transiting candidates. And there's over 1,500 candidates in multis, and those are the ones that are almost certainly real. And there are about 2,000 other candidates too, most of which are real. And the multiple planet systems tell us both about the planets, because we can get masses as well as radii, but also about the architecture, how close planetary systems are, how common flat systems are. And Kepler 11 was really important in a lot of firsts in terms of the high, close number of planets that verified and getting the low densities of all these planets. So the only word I could think of to describe it was supercalifragilisticexpialidocious. And on that, I'm going to open the floor for questions. Thank you.